Fredrikson. Matt got his PhD from the University of Wisconsin, and he's now an assistant professor at CMU. And he's done very interesting work in a broad range of topics related to security and in particular to privacy. So please go ahead.
Thanks. On now? Okay, thanks. Okay, before I dive in, I want to mention that this is a joint effort between my students Emily, Klaus, and Sam, and I co-advise Georg with Anupam, and his two postdocs, Peter and Shayak, they're out with him at our Silicon Valley campus. So you've already seen a few talks on machine learning and the various problems that can arise when you apply machine learning in certain situations. So I don't need to belabor the point that these systems are everywhere and they're being used in some important contexts too much. But in particular, machine learning and these sort of data-driven systems, and by that I mean systems that sort of depend for their core functionality on data that comes from individuals, right, are being used in domains like credit rating, healthcare, education, law enforcement. And there's a lot of excitement about this. The benefits are certainly all over the various headlines that you see. But there are also some concerns that crop up, in particular when we look at these applications that work with people's personal information. Right? And the sort of cause of some of this concern is the fact that these systems tend to be opaque. So what do I mean by that? Well, you give these systems some data from the users, train up a model, and then use that model to sort of make predictions or decisions about these people. And you really have no idea what's going on inside of this black box, right? The model that you get from training. It's not like somebody sat down and wrote this model by hand and sort of used deduction to reason about what its behavior is going to be. And it can be pretty difficult to sort of peer inside of these systems and figure out, what caused the decisions to happen, right? And so when this sort of touches on privacy and fairness, there's a risk that users can be harmed. So first, a few examples. Back around 2012 or 2013, there's this article in the New York Times about Target, that's a sort of big box retailer in the United States, who had developed a predictive model to try and figure out which of their customers were pregnant, right? And so they used their shopping basket history and narrowed it down to about 25 products that when you sort of put them together in the right way, came up with a pretty accurate pregnancy prediction score. And this sort of came to a head, or I guess the anecdotal story that drove the New York Times article was this 16-year-old girl in Minnesota who started receiving advertisements through the mail for baby-related items. Right? And so her father sort of looked at her mail and he was not pleased, but he was mainly unhappy with Target because he was absolutely convinced that there's no way his daughter is pregnant. So he calls him up, he says, "Are you crazy? What are you doing? I know what happens in my house, right? My daughter isn't pregnant, stop sending these." And I guess a week later he called back, a little sheepish, and had to apologize and gave them credit for making a correct inference in this case. Right? So these sorts of systems can create uncomfortable situations when they sort of learn private information about people and then sort of do things that affect your life with that. Much more recently, in fact earlier this month, you might have seen this headline about Amazon scrapping some secret AI recruiting tool that was biased against female applicants. Right? So they had over the course of 5 or 10 years, collected a whole bunch of data from people's job applications and who they hired and how well they did. And they were going to try and build a model to screen future applicants. They never quite got there, and this project is done now because they observed that it seemed to be unfairly biased against female applicants. Right? So what's going on here? Right? Why did this happen? Well, it turned out that most of their training data was for men, right? Like most tech companies, the majority of their workforce is male, so they just didn't have very much female training data. And whatever sort of application or whatever training method they used to build this filter, basically learned to associate features that are associated with women with negative outcomes, right? So they found that if a resume said the word woman in it, like that counted against their score. If they went to an all-women's college, that would also count against their score, and they didn't know what to do, right? So, several years of effort, probably lots of resources and so forth down the tubes because they sort of spotted this bug too late and didn't know how to fix it, right? So better safe than sorry. So the sort of focus of this talk is based on the view that you can understand both of these problems as a type of sort of inappropriate use of protected information, right? So in the case of fairness or discrimination, we could think of this as the use of race or gender for things like employment decisions, right? And in some cases, there can be exceptional cases where you can actually use features like this in these contexts. For example, US law has a business necessity loophole where if you can justify that the way that you use one of these variables has a business cause or reason, then it's okay. But in general, it still comes down to how you use these protected information types. And in privacy, as we saw, you might not want to use health information or information about people's political background for marketing, right? A lot of people would view that as a violation of their privacy. And there are similar kinds of exceptional cases that you can talk about that come from like this theory of contextual privacy to sort of make exceptions where necessary. Okay, and the sort of point here is that when these things happen by accident, this is a bug, right? So it was definitely a bug for Amazon when they figured out that their employment filter was biased against women. In the case of Target, that wasn't actually a bug, that was a feature. They had designed the model to predict pregnancy very intentionally. But as we showed in the CCS paper, and I'll get to a little bit later, these sorts of things can happen naturally by accident when you train machine learning models, and it can be difficult to tell when you might be using information like this. So the work that I'll talk about today sort of centers around methods for dealing with these instances of inappropriate information use, right? So ways of detecting when it occurs, and using information that you got during this detection to provide diagnostic information for developers, or in some cases automatically repair the system to remove the harmful effects whenever that's feasible. Okay. So for the rest of the talk, I'll spend some time sort of formalizing exactly what I mean by inappropriate information use, and then show how we can apply that definition to classifiers and do useful things. And then we'll generalize this all to continuous domains, so things like regression models that operate on real valued variables. And then I'll close up with some sort of ongoing and future work on nonlinear continuous models, think neural networks, and some interesting applications of those. Okay. All right, so we'll start by talking about explicit information use. Right, so what do we mean by that? Well, say that you have a classifier, and it's a black box. We don't know what it does, but the sort of ground truth is that it only uses income. But we want to figure out which of the two sort of input variables that we've given it, age and income, are actually used to inform this decision. So the sort of first cut approach that a lot of people might think to take would be to take samples from the training data, give them to the classifier, and see if there's any kind of a correlation between age and the decision, right? So that's not really going to work in most cases, or in particular in cases like this, where the two input variables are statistically associated, right? So age and income aren't independent variables. The older you are, the more money you tend to make, sort of on average. So if you tried to make this inference just by looking at the input-output behavior over the natural distribution, it'd be difficult or impossible to tell whether age was actually being used. You'd still see a correlation, right? So what you have to do is perform a causal intervention, right? So effectively what you're after is something about the behavior of the model, right? You want to know if the model actually sort of makes effective use of the age variable. And the way to go about this is sort of keep income fixed and give age a bunch of different values, see if the decision changes. In this case, it did not. Then do the same thing to income. All right, so keep age fixed and then give it different incomes, and you'll see that the decision changes. Why is this? It's essentially information flow, right? There's interference between income and decision, and we've tested this in this sort of black box way through the intervention. The sort of way that it differs from how you might sort of understand information flow is that we're interested in quantifying sort of the effect of age and income when the classifier is applied to the distribution that we're interested in, right? So in this case, people who are likely to apply for credit for whatever financial institution, right? And so the way to do the intervention is when you keep something fixed, you sample the intervened variable from the marginal distribution of the population that you care about, right? And then sort of quantify the probability that the outcome changes under that intervention. Okay. Yeah.
What happens when I'm like thinking, let's say somebody's applying for a loan, and income is completely indirectly relevant to whether you can pay off your loan. It may indirectly cause a bias for age. Is it still appropriate to rule age out in this way? What do you do in this case where sure it's correlated, but it's too bad?
Yeah. Sorry. So that's a really good question. And I think that's sort of beyond the realm of what a computer scientist can definitively say. So as I said before, age and income are definitely correlated. For something like a credit classifier, income is almost certainly going to be justified, right? If I want to take a loan out, how much money I make is relevant to that decision. I can say that there's a business necessity. If it happens to be correlated with age, right, then I say, well, I'm not actually using age, I'm using income, and there's a very good reason for that, right? Yeah, so there's this disparate impact doctrine that the U.S. and Europe, mostly base their laws on, and it has this necessity exception that would apply here. Yep.
Matt, another question.
Yes.
Could you also fix your training data in the sense get rid of some of the sensitive information to retrain the classifier?
Yeah, so that's a very good question. In this case, it's not clear exactly what you would do there. Like if you censored age out of the training data, you would probably end up with exactly the same classifier because it doesn't use age. Another thing you could consider doing is breaking the correlation in the training data between age and income, sort of resampling one of the columns from the marginal. There are reasons you might not want to do that. Some correlations might be useful and sort of don't manifest in harmful behavior. And yeah, that's it. Yep. Okay. So a more challenging case comes about where the sort of sensitive variable that we're interested in isn't explicitly provided as an input to the model, right? So if we have the same kind of classifier for credit decisions, we might say, it takes inputs that characterize the number of years that somebody's been in the same job, whether they've got a mortgage out and what their income is and so forth. And it can sort of combine all of these to create a proxy for age that then becomes influential on the decision, right? And in these cases, depending on the sort of nature of that proxy, it may or may not be justified, okay? If it's totally based on income, probably fine. But if it's like, the number of years that you've been in the same job, whether you're a widower or something like this, you probably want to do something about that, or at least realize that the decisions that you're making are informed in that way, right? And so that's the sort of challenge that we're setting out to address. And sort of another way to think about it is we want to characterize a set of behaviors that correspond to when the program infers this protected information type from other variables and then uses it in an influential way to form its outputs. Okay? So what do I mean by this? We'll sort of start by examples. So first of all, explicit use is definitely proxy use. We still care about actually just using the variable in a straightforward way. But the whole point of this is to characterize inferred use. So if we're looking at some of the other variables and finding a proxy for age, then we definitely want that to be proxy use as well, right? we have to be a little bit careful here because not all kinds of inferred sort of proxies in the program are necessarily of interest. For example, if I had kind of a dumb program like this that inferred the same proxy twice and gave exactly the same outcomes, then I'm probably, like, this won't actually harm anybody, so we don't want to think of this as a proxy use, right? So whatever the inferred value is, whatever form it takes in the program, it has to be influential on the program's outputs, okay? Right, another sort of subtlety. So we insist on two-sided statistical associations, right? So I've sort of led you to thinking about a proxy as some computation that is, correlated or associated with a random variable, but it's not enough to just say, if I can predict the private variable from the proxy, then this is potentially dangerous or harmful. Right? You want to be able to go the other way as well and say that I can, from the proxy, from the protected information type, I could predict the outcome of the proxy. And so, a quick example to see why this is important. If you think about a really simple kind of computation that looks at somebody's postal code to determine which state they live in, so they can send out an appropriate ad flyer, right? Well, at least in the United States, zip code can oftentimes predict race, right? But this isn't necessarily true the other way around. If I know your race, I can't predict what postal code you're in, right? And if we allowed this sort of one-sided association, then we would deem all instances that look sort of simple and benign like this as potentially dangerous proxy use, and this isn't what we're after. Okay, so final sort of example, if we look at this simplified sort of extract from this Amazon anecdote that I mentioned earlier. So we're going to test whether the applicant went to a women's college. If yes, then we're going to say, okay, is this person likely to actually be interested in the job, right? Did they just sort of put this app out or give it to us because we're like a safety option, they're overqualified, or are they somebody who's likely to actually come to an interview and accept a position if offered? So if you went to women's college and you're interested, then we're going to reject your app. Otherwise, if you went to the women's college and you're not interested, then we'll accept your app. Right? And for men, it's sort of the opposite way around. So what's going on here? Well, we're definitely still using the fact that you went to women's college and are therefore likely to be female to sort of inform the behavior of the model. But depending on how you do this test, you can sort of set this up so that there's no association between gender and the final outcome of the model, right, to sort of appreciate. So this is kind of an important point that just mere output association is not necessary for proxy use because of examples like this where you can actually kind of mask the effects of the inference and use of the protected information, right? So let's formalize this a bit. The way we do this is by defining a set of sort of axioms that seem natural and appropriate for the situation, and they correspond roughly to the examples I showed you. So the first axiom says that if I directly take in the protected variable and use it in the model, that's proxy use. Pre-processing basically says that if I infer a protected piece of information, right, and my behavior is equivalent to some other function that takes that protected information indirectly, some function of my inputs, then I have proxy use. Okay. Third dummy basically says if I already have proxy use and then I take in some variable and don't do anything with it, I still have proxy use. And the fourth independent says that if the function's inputs are independent of the protected information type, right, then there's no way for me to make inferences about it. Okay, so there's no possible way for me to have proxy use. Okay. So this is the sort of countervailing axiom. The rest characterize what we're after. This one characterizes what we absolutely don't want. So these seem pretty natural. Are there any that people disagree with? Think they're fishy? No? Yeah?
I'm just wondering what influential means here. Is that something you quantify?
So for this purpose, think of influential as actually interfering with the output. So having an information flow from the input to the output of the function.
So no matter how tiny the influence is,
Yes, we'll relax this later and do a quantitative definition, but for now it's, yeah.
Is X the sample of 0?
Is X a sample of Z?
Yeah, what is X? Is Z and X are not bounded?
X and Z are just random variables. Here we're not making any other assumptions about them. They might be associated and they might not be, right? Except for like an independence where we would assume that Z is independent of all of the inputs of the function. Yep. Yeah?
The first axiom, is it proxy use or explicit use? I'm trying to figure out how the term is used in this axioms that follow.
So you're saying axiom 1?
Is axiom 1 defining the notion of explicit use or proxy use?
It is defining the sort of special case of proxy use that is explicit use. Yeah. Yep. Okay. Well, the bad news is that these are actually inconsistent. There is no sort of definition that actually captures all these. And the intuition is that, because we accept preprocessing, we have to preserve proxy use under different kinds of function composition, right? But whatever happens after you sort of input this composed information can actually cancel out the effects of that proxy, and this leads to a contradiction, right? So if you consider 3 variables, x, y, z, they're all pairwise independent, but y is identical to the exclusive OR of x and z, right? Then certainly the function that takes the exclusive OR of y and z makes proxy use of z. That's explicit use. And so does a function that simply adds x and does nothing with it. Dummy. By preprocessing, making use of this fact that y is identical to x exclusive OR z, right? We can say that a double prime also makes proxy use of the protected variable, right? This contradicts with our assumption that x and z are independent because the z cancels out, and that's where you get the contradiction. Okay? So what do we do? Well, the approach that we took was to sort of relax what we're after, right? So these extensional proxy use axioms are nice. They characterize things in sort of pure functional terms, but they're never going to work. So we create a syntactic definition, right, where we, instead of using sort of pure functional composition, we introduce a notion of composition that is sort of based on how the program is represented syntactically. And then the sort of upshot is that to detect and do anything about proxy use, we actually have to look at the program that implements the function, right? So if we want to models as programs, we need a language. Luckily, machine learning models tend to be very simple programs, although they're oftentimes large. So for the purposes of this talk, we just assume a fairly straightforward expression language that has operations and if-then-else terms, because we do a lot of decision tree examples. And if we want to talk about things like the output of one of these expressions is a random variable, we have to sort of lift the semantics distributionally. So how do we do this? Well, we always imagine running models on instances that were taken from the target distribution, right? Whatever our test distribution is, that's our input distribution. So we can think of expressions as corresponding to random variables that take instances to values, right? And we can sort of imagine a joint distribution that has components for all of the input variables and all of the expressions inside of the model, right? We'll frequently sort of marginalize this and talk about just the distribution of some subterm in our machine learning model and so forth. Okay. So then the notion of composition that we use is pretty straightforward. So you can think of sort of adding a hole somewhere in the original program, right, and substituting in some fresh variable and plucking out the whatever term appeared there, right? And then a proxy is simply given by some decomposition where the thing inside the hole, the P1, is associated with the random variable. Okay. So in our example from before, women's college, obviously a proxy for your gender being female, and so forth. Okay. And then what does it mean to use a proxy? Well, all that we require is any influence whatsoever, right? So we just have to be able to change the outcome of the sort of outer encompassing program, and that characterizes use for us. So putting this together, our definition of proxy use says that if we have some, so if we're given a decomposition, it is an instance of proxy use if the P1 is associated with Z and it's influential on the outcome, right? And this is actually pretty close to the intuition from earlier, satisfies similar axioms. Dummy and independence are pretty much the same, but all of the others use this program decomposition instead of functional composition. Yep.
You don't need to assume you work with decision trees, right?
No, yes, yeah. So in the CCS paper, we have a slightly richer language than what I showed you. All the examples are decision trees because they're easy to write down, and we'll generalize this to more things later on. Yep. Okay, so as I said before, it's probably a little too strict to require or to allow any sort of influence or association to count as proxy use. So we relax this and give a quantitative definition where epsilon corresponds to some threshold on association and delta to influence. It really doesn't matter what sort of measure of association we use, as long as it is invariant under renamings of the values and characterizes two-sided statistical relationship between the variables. Right? So I think we use like mutual information or some way of normalizing it. Seems to do pretty well. Okay, and then we say that a program has proxy use if there exists a decomposition that satisfies this definition. Right. So a few words about how we actually quantify the influence of a subprogram. Recall from before, we intervened to measure the sort of causal influence of an input on the program's output. We intervened on an input variable and sampled from the marginal distribution of the corresponding component. Here we're not working with input variables, so if we have a decomposition, we sort of talk about intervening on the subterm that is our potential proxy. And all this means is we just run this program on an independent sample from the input distribution, right? So there's no correlation between the sort of sample that we're running the subprogram on and the sample that we're running the outer program on, right? That corresponds to this notion of causal intervention. Okay, and then we measure the sort of divergence in the outputs between the original program run on one IAD sample and this intervened version. Okay. All right, so to detect this, it's actually pretty straightforward. For a lot of models, you can just do sort of a naive brute force thing where you enumerate all the sub-expressions and then do this like n-squared sort of influence measurement to determine the potential proxies. That works well for decision trees and some random forests. It doesn't scale to really big things, even moderately big random forests. So one of the students is framing this as a probabilistic model checking problem. And seems to be making pretty good progress on that front, right? Yeah.
So this random variable, the sample, from what distribution is the discrete distribution? Or?
Think of it as the training and testing distribution, right? We assume that those are the same. Yeah.
But when you're sampling and running the program with this, right, computing the expectation, but I guess you can do. Does it have to be approximate inference, so you can compute it exactly, or? If you're given the distribution.
I see. So you're asking if I'm doing this by sampling, right? There might be some inaccuracy in my detection. Yeah, that's absolutely the case. Do this properly. You probably want to figure out what the probability of a false positive or false negative is, and then work out the p-values so that you can actually have confidence. That's sort of a down in the weeds orthogonal detail that is in our long appendix on archive if you're interested in that.
The number of samples are connected to the epsilon and delta somehow?
So yes, the number of samples will be absolutely connected to epsilon and delta. I don't recall exactly like what the relationship is, but if you have a very small epsilon or delta, you don't need very many samples to detect this. If you have a large one, you probably, yeah, yep. Okay. then what do we actually do about this? How do we remove a proxy use violation, so to speak? Well, we haven't looked at this problem too much. One really simple thing is just to replace the proxy with a constant, probably whatever the statistical mode of the sort of term's output is. That works okay some of the time, but I'm sure that there are better ways to do that. We'll get to it eventually. Yeah. Okay, so one of the nice things about this definition is that if you observe some kind of a privacy or fairness issue, or you suspect one, you can sort of run these algorithms and look for instances of these proxies. And if you find one, you sort of have this witness that demonstrates that the system is doing something inappropriate with the information you gave it, right? And it tells you exactly where to look in the model to sort of understand what's going on and possibly fix it. Right? And so we have a little bit of experience with this. I won't spend too much time on it. You can read the CCS paper, but what we basically wanted to confirm in the initial work here was that like proxy use actually happens naturally, right? If you're not trying, you sort of get these issues cropping up organically in machine learning models. So we took some benchmark data sets, things from like the UCI repository, and censored some of the rows before training. So in the adult data set, we, for example, censored marital status, trained up a bunch of trees, and then looked to see if it inferred a proxy for marital status, because that actually turns out to be a fairly predictive feature for this data set, right? And we absolutely did find instances of that pretty much every time we'd resample and train. And I think like on average for this model, we get 83 or 84% accuracy without marital status. And if you just remove every proxy for it, replace with a constant, you don't really hurt the accuracy that much. For other data sets, that wasn't necessarily the case. So we found a really influential proxy for the wife's religion in a data set that looked at like contraceptive use in Indonesia. Don't ask me why. It was actually a pretty tough data set to classify before, and apparently whatever the wife's religion was, I was very informative of that, so not such a good idea in this case to just sort of replace the proxy with a constant, but we'll get to better techniques later on. Okay, so now that we've seen how this works for classifiers, we sort of agree on the definition. I will generalize to continuous models. In particular, we'll look at linear regression models, right? Really simple things. The model itself is comprised of a bunch of coefficients, and each coefficient is multiplied with the input feature summed up to produce a final prediction, right? These are simple. I know like all of the sort of enthusiasm and hype is around things like deep neural networks now, but linear models are still very frequently used in a lot of domains, for example, credit scoring, because they are interpretable, right? So our notion of influence from before was sort of based on this program decomposition and comparing whether the outputs are identical under intervention. So in this setting, we can think about generalizing by replacing this inequality or this negated equality with the expected squared error in the model under intervention. Right? Another way to think about this is for classifiers, you think about using 0-1 loss. For regression models, typically the loss is the squared error, right? But the question now is, what are the decompositions, right? So do we want to do something kind of simple and straightforward, like thinking of all the variables as individual terms or maybe combinations of them? Or do we care about sort of, fractions of some of the terms, right? Could very well turn out that some portion, some component of a combination of variables is a stronger proxy than any of the variables times coefficients themselves, right? And if that's the case, then we're going to be interested in finding these. So what we use here, call these components, basically consist of a vector of reals between 0 and 1 that, specify how much of each term we actually want to take for our subprogram. Okay. And the nice thing about this is the influence that I showed you before just works out to be proportional to the variance of that component, right? This is really nice and simple. Okay, so these are linear models. We don't really care about nonlinear correlations anymore. We can just use the covariance to reason about association, right? And one other nice property about this is you can actually interpret random variables in this vector space where covariance is an inner product, right? So you can think of the association between two random variables as a sort of angle between them in this vector space, and their influence, the variance, as corresponding to the norm of the corresponding vector, right? So if we think of this blue line as representing our delta for influence on our proxies, and theta is corresponding to our epsilon sort of association threshold, right, then all of the proxies for this random variable z would sort of reside in this region where our association is rather high and our influence is high enough to be above the threshold. Okay? And then all of the components of the regression model are sort of linear combinations of the two terms on component, and you can sort of think of searching for proxies by trying to find a component that lies outside of your radius and is within the angle that you need for association. Okay? And this turns out to be an optimization problem. It's non-convex, but still often tractable. You can make it convex and therefore way more tractable by sort of finding an objective that over-approximates the true objective that corresponds to influence. Okay, so I'll finish up quickly here by talking about sort of extensions to more complex and interesting models. So we've heard a lot about neural nets so far. We're interested in feed-forward neural networks, and in particular convolutional nets, right? How do these work? So you've got a bunch of convolutional filters sequenced with these max pooling operations that sort of help prevent overfitting. And you sort of learn a bunch of features along the way that correspond to patterns in the input instance, and then follow up with some fully connected layers that sort of correspond to the classification logic that you're going to use over these visual features that you've learned from the convolutional layers, right? So we sort of think about decomposing neural networks into feature extractors and classifiers. You can sort of frame this decomposition at any layer of the network. You can sort of slice up until the very end and say, I'm going to think of the neural network as basically a linear classifier that takes in as features all the things that I've computed from earlier layers. Or you can do this even earlier in the network, but then the classifier that you have to reason over is nonlinear and a little more difficult, right? So the influence measure that we use here basically takes this perspective to heart and is based on sort of one of these slices. You choose a slice in the network, how you're going to decompose into feature, extractor, and classifier, and then integrate over the gradient of the classifier on the feature values that are computed up until that point. Okay, and this is all done so this integration happens over some distribution that you're interested in characterizing, right? So for example, this could be a point distribution, a single instance, and what this would give us is a characterization of how influential the features of one particular instance were, right? If the distribution were the entire training data, then we would sort of get an average measure of how influential features at some layer of the network were over the entire training distribution. Okay? And this satisfies some natural axioms as well that this sort of gives us confidence that this is a reasonable thing to use. Okay? So there are a couple of things that we're looking at applying this to. So I'll tell you about some problems and then give you a hint at sort of how we're going about addressing them. So one is kind of strange. So this picture was given to a pre-trained ImageNet classifier, which determined that this was a picture of a basketball with 73% confidence, right? It's not a basketball, it's Usain Bolt. Why did it think that? Well, we'll get to that in a minute. Similarly, this picture of a gentleman from the Chinese Olympic soccer team was classified as a ping pong ball with 37% accuracy, right? But white guys who are in athletic gear just get called ball players, okay? So this is kind of concerning. It seems like the model has learned to stereotype somehow. Okay. Yeah, and see this paper by Stock and Sis at Facebook for a few more examples. These were not from that paper. I just found these after like 10 minutes of Google image searching until I found things that ImageNet misclassified, right? So another problem that our sort of hypothesis is closely related to this is known as bias amplification. So there's a paper, I think one best paper at EMNLP earlier this year that was looking at image tagging models. So the sort of learning goal is to figure out what activity is taking place in a picture, who's doing it, a man or a woman, what food they're cooking, and so forth. And what they found was that in the training data, about 33% of the images tagged as cooking have men in them, right? And in the predictions that the model gave, only 16% of the agent roles in cooking images were labeled as men. So there's sort of a bias skewed distribution to begin with, right? Men are definitely in the minority in the training data, and the model learns to sort of amplify that somehow, okay? So the question is, what's going on here, right? So if we go back to this sort of stereotype predictions scenario, we applied our sort of influence measure to construct an explanation for why the model thought that this was a basketball, right? So we sort of sliced at the very end of the network to find the most influential features given before the softmax layer, and then visualized the receptive fields of those features, right? And as you can see, the top 5% most influential features for this classification are just Usain Bolt's face, right? If you sort of, yeah.
I don't think it's Usain Bolt. It's Maurice Green.
The JPEG file name says Usain Bolt. That's the only reason I think that. Okay, thanks.
You're saying Jamaica.
Yeah. Does it? So it does, okay. The top 25% most influential features still focus a lot on the person in the center, but now we also pick up like the knee of the guy over there and some bits of the audience, right? So it sort of intuitively seems like maybe what's happening is in a lot of pictures that are labeled basketball, there are pictures of dark-skinned men in athletic gear and sort of, you know, blurred out portions of the audience in the background, and sort of learning that these are weakly correlated with the label basketball. So it kind of learns these weak features that are maybe helpful sometimes in correctly classifying basketball. And then in these other cases, sort of misappropriating those features, right, to make incorrect predictions, right? So you can really think of these features as proxies somehow, right, that are being used in causing mistakes in the classifications. So how is this related to the bias amplification problem that I told you about? Well, when we first started looking at bias amplification, we were a little discouraged. They actually didn't seem all that related. So we started out by sort of thinking about synthetic data, and what we did was derive the Bayes optimal classifier for some sort of Gaussian binary classification problem, right? And what we're seeing here is the behavior of the classifier as the statistical distance between the class means increases or decreases, right? On the y-axis, we have the sort of prior class probability, how likely the training data instances are to be class 0 or class 1. And what you notice is that, so this is the Bayes optimal classifier. You really can't do any better than this on this data. As the data means get closer, right, the bias sort of shoots up very rapidly. Okay, so there's something essential about this. When the data isn't well separated and it's biased, what the model or what the learning algorithm does sort of always revert to the prior mode. Okay. And there's nothing you can do about this unless you wanted to sacrifice some accuracy. Okay? So at first glance, it seems like bias amplification is maybe sort of a data problem, and there's nothing we can do about it when we look at the algorithm and the model. We took a closer look and trained using gradient descent, a linear classifier on the same data. Right? In this case, the data was unbiased. So the prior was 0.5 probability to be in either class. Right, and what we saw was that there was, significant bias even in this case, right? So the Bayes optimal classifier would have never produced bias here, but gradient descent does, right? And this is worse the less data you have. So if you have a very small amount of data, then there's quite a bit of bias. As you get more, you get closer to the sort of Bayes optimal classifier, right? The reason is gradient descent will converge to the Bayes optimal if you give it sort of infinite amount of data, but that's not what we had here, okay? And the sort of turns out that the cause of this is a kind of inductive bias in gradient descent. So the more sort of weak features that you have, the more weakly correlated things for a particular class, the greater this sort of bias amplification effect is. And the cause is that gradient descent seems to overestimate the importance of these weakly correlated features when you don't give it enough data. Right, so that's what this second plot shows, is the sort of difference between the weight that the gradient descent learner inferred for one of the coefficients and what the Bayes optimal sort of value for that weight was. And as the data gets smaller, you can see that it overestimates it quite substantially. Right? The takeaway here is larger weights imply more influence. So to us, this suggested that you might actually be able to get some traction with some kind of feature selection. So that's what our sort of first idea was, just kill whatever the weak features are and see if that helps the bias. We frame this as a grid search where you want to minimize the bias of the resulting classifier by finding the sort of right balance between influential positive and negative features for each class, right, subject to not making the classification accuracy any worse. Okay. And anything that's less influential than alpha or more influential than beta, sort of in between, just gets thrown out. Okay? So we've tried this on a few models, sort of just to test the intuition out. One we tried on Celeb A, which is a fairly large data set of pictures of celebrities with labels like eyeglasses, bangs, and pointy nose, about 40 binary features. We looked at a model that predicted the attractive binary feature, right? Which in the data wasn't very biased. About 50% of the people were labeled attractive, 50 not. But the predictions were fairly biased, about 8%, and reasonable accuracy. We did this simple sort of feature selection fix. We eliminated pretty much all of the bias and improved the accuracy a little bit, right? This is promising, and we've applied this to several other data sets, another neural network, and a whole bunch of sort of benchmark linear models. And you can pretty much always eliminate some amount of the bias, and you rarely hurt accuracy when you do this. So it seems like this might be a good way of sort of explaining and mitigating the bias amplification and stereotyping problems sort of at the same time. All right, I think I'm over on time, so I'll finish here and take questions.
Okay, thank you very much. Who wants to go first? Yeah, in the back, yeah.
So the first part of the talk seemed to be, it reminded me a lot of Judea Pearl's original work on causality in a graphical model. Can you say how you relate to that, or? Yeah,
so the kind of causal influence measure that we wanted to characterize exactly corresponded to this sort of notion of but-for causality that Judea Pearl studied over the years. Initially, we were sort of considering looking at this as a problem of actual cause, and after spending a couple months going back and forth and trying to figure out which definition of actual cause or whatever to use, decided against that. But yeah.
And that question here, yeah. So I guess you consider like the white box setting, right? Can you say anything about the black box setting? Can one do anything?
Yeah. So the original explicit use slide that I had up there had a citation for paper from Oakland 2016. That was all about black box information usage, right? Which input variables are influential on the output and how much. We were at first interested in doing something black box. It's a lot nicer to be able to work in that setting, and you can sort of think of a richer class of use cases, that have to do with external audit and so forth. I think this inconsistency result in the extensional axiomization says that we probably can't get very much traction with the black box analysis. But I think it could still be interesting to look for cases where, for example, you can sort of like have an over-proximate test or a very sensitive test in the black box setting that you can then sort of later refine with limited or partial white box information. And techniques that do that, I think, could be useful for outsiders who don't have access to Amazon's models or Google's models or so forth. Yep.
Any other questions? So I have a question which is possibly stupid, and just tell me so. I was wondering, much of the work seems to assume that we don't want to discriminate, for instance, or don't want to introduce false labels, and then you have ways of detecting that. Let's assume somebody wants to, right? The law prevents you from discriminating against age, but you want to do this anyway, and so you try to find substitutes. So does your work enable that kind of cheating in a sense?
That's an excellent question. Okay, so first of all, the goal of this is not to sort of prevent discrimination or present a definition that defines what it means to discriminate in a model. I think that's kind of a misguided sort of effort. Our whole goal here is to provide sort of techniques and tools that well-intentioned people who want to do the right thing and sort of understand what their models are up to can use to get at that. That said, if your goal is to discriminate, I don't think you need much help. I think that if there is an association to be had, there's probably a machine learning library or algorithm out there that you can use to take advantage of it. And as far as keeping it hidden or masking it, I don't know. Could be an interesting thing to think about. Another class of attack paper to submit to Oakland and NDSS. But yeah, I haven't thought about that too much. Yeah.
Okay, thank you. So let's thank Matt again.